Hello everyone. In this video, I wanted to just go into the details of transmission and reflection off of a step potential. So we set up the basics in our live lecture where we said we have a step potential, goes for on the left it's 0, on the right it's V naught. We have some incoming wave from the left traveling to the right with an energy E, which is above V naught. And in the two regions, we write down the most general possible solutions, where we can have left going or right going and left going waves there, left going and right going waves here. But we say, given the physical problem that we're doing, we're thinking of this problem, we're trying to imagine a beam coming from the left traveling to the right, and it's either bouncing, being reflected backwards off this barrier, or some of it is being transmitted to the right. We don't want to have something over here traveling to the left, because that would mean something sort of reflected at infinity, and that's just not the physical situation we have. We're imagining our sources all the way at the left at negative infinity. So this term we're not going to write down just because of the physical problem that we're considering. And then what we have is this is basically our incoming amplitude. This will be our reflected amplitude. And this will be our transmitted amplitude. And so we're going to do what we have been doing with the wave function. We're going to put these together, match up the solutions at the boundary, and see what we get for the coefficients. So when we write that down, we can match these two things up at x equals 0. That's nice and easy because e to the 0 is 1. So that gives us that a plus b equals c. So that's matching up the function at the boundary. Then if we match up the derivative at the boundary, we get a factors of ik or minus ik, or actually this should be a k prime, different k. Then we get ika minus ikb equals ik prime c. And what were k and k prime? Those are, remember, k is going to be just square root 2me over h bar, and k prime is similar, but it's e minus v naught for h bar. So that's k and k prime. And then it looks like we have two equations, but three unknowns. But there's really only two unknowns here that we're actually interested in this case. We are interested in the ratio of the reflected to the incoming and the ratio of the transmitted to the incoming. So the things that we're actually going to want to compute are, and we're interested really in probability, which remember is the wave function squared. So we're interested, for example, in the reflected probability, which is going to be absolute magnitude squared of b over absolute magnitude squared of a, and the transmitted probability, which will be magnitude c squared over magnitude a squared. But with one wrinkle for the transmitted case, in that the wave number is actually changing. So that changes the momentum of the particles. And so we want to make sure that we have sort of the same momentum going to the right side of the barrier as we do have incoming from the left of the barrier. We want to sort of match the rate of particles coming in, particles going out. Otherwise, we're sort of accumulating stuff at x equals 0, and that doesn't make sense. What we have to do here is just adjust for that by putting in a factor of k prime over k. We multiply this by k prime, this by k, then that matches things up nicely. And these are probabilities. What we should have automatically, but we can check it at the end, is that we should have that if we add up the probability of a particle being transmitted plus the probability of a particle being reflected, hopefully that's 100%. One of those two things has to happen. So now we just want to take these top two equations and rearrange them, solve for b and c in terms of a, and see what we get for these reflected and transmitted probabilities. So let's just put that in. So for example, B, we can rewrite this, B equals C minus A. We can take this second equation, pull out the IK, then we can say, okay, A minus B equals K prime over K times C. And then actually we can take this and let's see, the nicest thing we can do here, we want to get rid of one of these things. So what we can do is we can actually say, well, C is A plus B. So let's actually just plug that in here. Now we have A minus B equals K prime over K A plus B. That's getting pretty close to what we want. So now we have A minus B over A plus B. Let me clean that up. Equals K prime over K. And now we just want to kind of get rearrange this so we get the B on one side and the A on the other. We really want to solve for B over A, or just B in terms of A. But what we can do is we can kind of multiply this through. Actually, I maybe should have left it the other way around, because what we can do here is we can say, let me actually rewrite this a different way. We've got A minus K prime over KA, bring that to the left-hand side, equals B plus K prime over K, copy K, K, B. That's on the right-hand side. So this is a better way of writing this. I can rearrange this a bit. I could say B 1 plus K prime over K equals A 1 minus K prime over K, and now this looks much nicer. I have that B over A equals 1 minus K prime over K over 1 plus K prime over K. Or if I want to make this look a little nicer, I can multiply top and bottom by K and just get K minus K prime K plus. So that's B over A, which then we can pretty easily get the magnitude of B squared over the magnitude of A squared. There's nothing complex in here. So we'll save this. And then let me clear up some space, but we can similarly find, now that we've got that, it's easy to find C over A. Because again, we can start with C is A plus B. C over A is going to be 1 plus B over A. This is also, by the way, just really reinforcing that T plus R equals 1. And so we can write 1 plus, we've already solved for that, K minus K prime over K plus K. And we can actually rewrite this in a nicer way by just saying 1 is actually K plus K prime over K plus prime. And when we put that together, we get 2K over K plus prime. C over A, 2K, K plus K prime. And so that basically, these bottom two, this is what we want. This is now what we can get out of our equations. This gives us the transmitted probability and the reflected probability, and we can plug in the energies involved to find what K and K prime actually are, but it's actually easier to write it sort of in this form. Get K's first and then plug it in, and we can figure out reflected and transmitted probabilities. So this will then lead to next time I'll do the same thing, but for a barrier potential, and we'll look at tunneling.